Well, hello, chemists. It's Mrs. Slater. I told you that I would not be on video, and here I am on video. So hello through a computer screen. I miss you, and I'm excited to keep teaching you, but please let me know how you're doing and what questions you have, because we are going to keep going in this kind of crazy time. So without further ado, we are going to be getting into more reactions of organic compounds, and we finished up the reactions of the alkenes, and now we're going to be getting into the reactions that the alcohols undergo. So just be a little bit patient with me because this is brand new learning for me. I am trying to figure out how to do all this and have it all work. So I got to go back to where the beginning is at. Okay, so you're going to see me in one of the corners. I might have to move myself depending on where content is on my slides, but hi, I hope you're having a great day. And here we go, jumping into the deep end with the alcohol reactions. So this is, these are some of the things that we're going to be learning about in this chapter, and I'm going to be walking through each of them with you guys. Okay, so to kick it off, I need to figure out how to do this. I'm going to annotate here. I'm talking through what I'm doing. All right. So I'm going to move this down to the bottom as well. Okay, so just going back to what we learned earlier about the alcohols, we know that they are one of the classes of compounds that are made up primarily of carbons and hydrogens, but they also have that hydroxyl group. So if we look over here at our formula, isn't that fancy? I can just circle the general formula. So for every carbon that you've got, you're going to have twice as many hydrogens, and then I kind of think of the last two, where on alkanes you would have those last two hydrogens. Only one of them is going to be a hydrogen, and then the other one is going to be our hydroxyl group over here that makes our compound our alcohol. So just remembering some of the characteristics of alcohols. We know that, again, they're primarily carbons and hydrogens, but that oxygen in there is going to make a pretty big difference with a boiling point. Whoop, right there. So they're going to have higher boiling points than the alkanes, even the alkenes, but not quite as high as water. So when you think of, again, rubbing alcohol or something, it's going to evaporate pretty quickly compared to water. They are going to dissolve, and we talked about how the more polar a substance is, the better it is at dissolving, especially if they're smaller. So if we have a teeny little alcohol, it's going to dissolve really well. If we've got a gigantic alcohol with tons and tons of carbons and hydrogens, the region that's going to dissolve better is going to be the area with that hydroxyl group, because that's what makes our molecule polar. All right, let's see if I can figure out how to move to the next slide. Nope. I'm just drawing dots. Okie dokie, hold on here. Can turn it into the mouse. And I think, there we go. And I can erase. How about clear? There we go. Okay, so thank you for your patience with me figuring out how to do all of this. Now my eraser's on, I don't want that. I want to be able to draw again. Okay, so these are the reactions that we are gonna be doing and going over. I'm just gonna be focusing on the combustion and oxidation reactions for right now, because those will provide you with plenty of information for right now. So I'm going to kind of break it up a little bit, and we'll focus on the other reactions a little bit later. And I'm actually not going to be even going over every other reaction that's down there. So, we're going to kick off with combustion. And what have you learned this whole chapter with the alkanes and the alkenes? The exact same thing is going to be true for the alcohols. If we've got an excess supply of oxygen, again, let's make sure that I'm in my draw mode. Oopsie daisy. Oh, goodness. Oops, sorry. Okay. Nope, I don't want to draw lines. It's harder than it looks. Okay, so if we've got an excess supply of oxygen, we know that this is going to be complete combustion. My handwriting looks terrible, but hopefully you can read it. So it's complete combustion, and we know that any kind of complete combustion reaction is going to yield carbon dioxide and water molecules, and then these are going to be balanced, and we know also that they're exothermic, which is going to give us that negative delta H value. Along with that, I could ask you a question, or IB could ask you a question of what the products would be in an incomplete combustion reaction, and you know that if it was incomplete, then we would add the products of both carbon monoxide and just carbon, which again, both of those are going to be toxic substances. All right, so nothing too new with that other than the fact that alcohols also are good at combusting. And next up, oops, gotta clear it. We are going to be getting into those reactions with oh, I think it's going the opposite direction of what I want to do. There we go. Now we're going to start getting into reactions of the alcohols where they are being oxidized. This is a little bit more complicated than the combustion reactions, but I'm going to walk you through it step at a time, and you are welcome to watch this back as many times as you need to for it to make sense. Also, please know that you can shoot me any questions, send me an email, and I can respond to that. Okay, so we've got the degrees, and this is what we learned in that intro part of the organic chemistry unit. And so going over primary, secondary, and tertiary is absolutely essential when we are dealing with the oxidation reactions of our alcohols. So if you can remember, primary, secondary, and tertiary don't have to do with what, and I'm going to do our hydroxyl group on this side. It doesn't have to do with the carbon that's directly next to it, because if we did that, it would always seem like it's primary because there's only one carbon there. But we're looking at how many carbons are next to this carbon. So if we've got, for example, one carbon over here. So we've got, here's our functional group right here. Sorry about the weird circle. If its neighboring carbon is only next to one carbon, we're going to call that a primary alcohol. And so that would look more like if it's a 5 carbon, we're going to do that. And then again, the rest of it would be fully saturated just with hydrogens. This pen is kind of funny to use. So we're going to be drawing all the hydrogens around it like that. I'm not going to necessarily draw all the hydrogens for all the rest of the compounds. But this is going to be our primary. Our secondary alcohol, again, the carbon, so here's our OH. That carbon that it's next to has to be attached to 2 other carbons. So here's neighbor 1, here's neighbor 2, and now we're going to just draw the rest of our chain. We'll draw another carbon. I don't know, a couple other carbons down here. So now we've got a total of 5 carbons, and then we're just going to saturate it the rest of the way with hydrogens, which I am not going to draw in, but you can draw those in on your notes. For the tertiary, These are the ones where our hydroxyl group right here is going to have a carbon next to it. And this carbon has to be attached to 3 carbons. So now we've got 1, 2, 3, 4, and we can just do our 5th carbon over there, but this is going to be our 3rd degree, that's our 2nd degree, and this one up here was our primary. Okay, so remembering that stuff, we need to identify. Now we're going to do a little test, see how you do with this stuff. We are going to, whoops. Come on, what's going on? Ooh, I'm moving it. We are going to do a little bit of practicing with what degree each of these 3 types of compounds are. And again, these are going to be different types of compounds that we learned about in that intro part. So I want for you guys to maybe pause this for a second and draw out these functional groups, remembering what degree each one is. So go ahead and pause this for a moment, draw out those functional groups, and then identify the degree of each. And I'm going to help you out with that if you're having trouble. All right, so our aldehyde, if you remember, we're going to have, oh, whoopsie daisies. We are going to have our aldehyde that, again, remembering aldehydes and ketones, they are both just carbon double bonded to an oxygen. But where they're located in that chain, in the carbon chain, is going to be different. I always think that A is at the beginning of the alphabet, which is either the front end or the back end. And if we have our carbon double bonded to oxygen, either at the beginning or the front or the back end of our molecule, it's going to be an aldehyde. If it is in the middle, which the letter K is in the middle of our alphabet, then that's going to be a ketone. So when we've got an aldehyde, that is going to, we're going to have our R group over here, which just means the rest of our molecule. When it's an aldehyde, it's going to be ending our chain. When it's a ketone, our carbon double bonded to oxygen has to be in the middle of a chain. So we have to have carbons on either side of it. And then when you're looking at a carboxylic acid, I'm going to try to find some room here. It is going to be, so we've got our carbon, it's going to be double bonded to 1 oxygen above it, and it's going to have another oxygen next to it, which also has a hydrogen. So if we look at the degree of each of these ones, when we look at this essentially is our functional group right here. The carbon that it's attached to, it's only attached to 1. So we have to look at how many other carbons. And the only option that we've got over here is in the R group. So our aldehyde is always going to be primary. When we look down here, again, here's our functional group here attached to this carbon. And this carbon has 2 carbon neighbors. So this is going to be secondary. And then over here, our carboxylic acid, I didn't draw our R group over here, but here's our functional group over here of the carboxylic acid or the carboxyl group. And this carbon is only going to be able to be attached to 1 carbon from our R group, which means that this one is also 1st degree. So if you look at this, both our aldehyde and our carboxylic acid are going to be primary. Our ketone is going to be secondary. And again, just remember that we are going to be coming back to these. So the 2 primaries are aldehydes. So this is going to become really, really important as we go through this. Okay, I think I'm catching on to this. We'll see. Okay, look at this. Doesn't this look fun? This is what we're going to be going through, which there are a lot of reactions that happen in organic, and eventually we're going to kind of put them all together in this crazy flow chart. But right now, instead of focusing on what the heck is going on this slide, I'm going to just kind of start delving in to what happens with primary alcohols. So if we could draw a primary alcohol, I'm just going to start small. We'll do ethanol. Oopsies. I need to actually click on the drawing. Going to get it one of these times. All right, so we've got our 2 carbons. And again, it is however many carbons we've got. We're going to have double the number of hydrogens. So each carbon has 1, 2, 1, 2 attached to it, plus this one has another one. That's where the +1 comes from. And then on the other side, we're going to have OH. Well, when we oxidize something, what can happen is the super simplistic version of it is oxygen can be added. And essentially what's going to be happening in all of these is our carbons are going to basically gain a double bond relationship with an oxygen. So I'm going to draw something weird up above my arrow here, which I will interpret for you later. Really specifically, this is indicating that an oxidizing agent is present. And so what ends up happening is we're going to take our primary alcohol and we are going to, when it's exposed to our oxidizing agent, nothing is going to change about the part of the molecule from over here. It's only going to take place where it on the carbon where our hydroxyl group was directly connected to. So what's going to happen over here now, and we do not need to get into the mechanism of this, is this is now going to give us a carbon that's double bonded to an oxygen. And because this was primary before, it is going to end as a primary molecule. So this, again, this is our functional group. So that means that this carbon should only be bonded to 1 carbon. So this is actually going to be the end of our molecule here. And this is also primary. Well, this is our primary alcohol. And with the oxidizing agent, it got converted into this type of compound over here, which, if you would recognize from my question a few slides ago, this is an aldehyde. So a primary alcohol can get converted directly into an aldehyde. Now, I'm actually going to continue on this. I know my slideshow doesn't follow this exactly, but since I already have it all here on my slide, I'm going to actually continue. So if I've got this, we looked at another functional group, or sorry, another type of compound that's also primary. And what's kind of funny about this type of reaction is that if we take an aldehyde, and my arrow is going to be really funny here, I'm just going to continue it down below. If we continue to oxidize our aldehyde, we can make something else. And actually, I think I am going to get to that in a moment. Okay. All right, so here's some notes. You are welcome to take notes on this. I'm not going to stop too much because I just went over that. But again, the first step is just our primary alcohol getting oxidized by an oxidizing agent, and then that gets converted into an aldehyde. There's another stage that we're going to be getting into, and I think it's right about here. So again, primary alcohols are going to create an aldehyde, but if we continue providing them with an oxidizing agent, they can actually convert chemically into another type of compound. And I said what is the primary functional group, but it should be the primary compound. What compound from slide 11 did we write down that is also primary? It just happens to have a little bit more oxygen. Well, that is going to be a carboxylic acid. So when we look at this, if you guys look at this, this little chart right here, again, we're going to take our primary alcohol right here. And I showed you before, I wrote out the reaction, expose it to an oxidizing agent. That's going to give us our aldehyde. Now, if we continue that process and oxidize it even more, you're going to notice that this group stays, but down here, what used to be just a hydrogen is going to get converted into a hydroxyl group, and this whole thing together actually is our carboxyl group. So we go from a primary alcohol, this is really, and then we convert it into an aldehyde. And then we can go another step further and convert it into a carboxylic, oh goodness gracious, acid. Ooh, that was nice. Okay, so now it doesn't look quite so bad. All right, so this is kind of the two-step process that primary alcohols can go through. We're going to talk later about how we can actually purify both the aldehydes and the carboxylic acids, because if we have this whole process going on in one container, we don't like impure substances. So if I'm a manufacturer and I say that I'm selling an aldehyde, it better be pure. Same thing for carboxylic acid, it better be pure. So we're going to talk about how to do that in a little bit. Okay. All right, so now for secondary alcohols, we are going to get into what happens with those. I'm going to go back and then you can, whoa, sorry, one more. Okay, so our secondary alcohols, I'm going to go ahead and draw one of those for us. Again, we have to remember that our hydroxyl group is going to be next to a carbon, and this carbon has to be next to two other carbons. So I'm going to just use this one because it's the smallest molecule that we can have that is an alcohol that's secondary. Okay, so we've got this. Now, same thing as before. I'm going to draw my arrow with my oxidizing agent over it. This is just a generic symbol. And what's going to happen with this is same as before. So the only thing that's going to be impacted is the carbon that has my functional group of my hydroxyl directly attached to it. And it's just going to replace basically that hydroxyl group with a carboxyl group, or not. Nope, not a carboxyl. Sorry, yeah. A carbon double bonded to an oxygen, and everything else is going to remain intact. But if you would notice, so our 3 hydrogens are on that side. Our 3 hydrogens are going to stay intact over here. But what you need to notice is this carbon now has 1, 2, 3, 4 bonds around it. We know that it cannot exceed that. And so you're going to notice that this hydrogen has also gone away. And we don't need to worry about that as one of the other products because we're mainly focused on the organic compounds being created in this. So with this, my secondary alcohol got converted into this thing right here. And again, you can pause if you need to, but quiz yourself. What is the name of this compound where our carbon double bonded to our oxygen is in the middle of our molecule? Ask yourself, quiz yourself. That is a ketone. Okay. And this is all we're able to do for the secondary. They just go through that one step here. When they're being oxidized, we cannot further oxidize them into anything else. So just secondary goes into ketone. Okay, so here's a little summary on that. Again, just those R groups each represent the rest of a molecule that contained carbon. So again, our hydroxyl is next to a carbon that has 2 carbon neighbors. And then that just goes into a carboxyl, or goodness, a ketone. Okay. And that's the only reaction. Okay, here's a specific example. So if we have propan 2-ol, where our hydroxyl group is off of that second carbon, gets oxidized, again, that OH group is going to get replaced just with a double bond to oxygen. And because there's a double bond here, that hydrogen has to disappear. And again, this is the molecule that we're going to be focusing on here. And this is the one, because there's 3 carbons in our main chain here as well, it's going to be prop. But because there's a ketone, or it becomes a ketone, we're going to change that ending to -one. Okay. When we look at these lovely tertiary, this means that we've got our carbon who's got our hydroxyl group, should be attached to 3 carbons. And again, this is kind of the simplistic, most simplistic one that I can draw. Again, all those hydrogens. Takes a while to draw. Okay, there we go. Now, if you guys think of what happened with the oxidizing of them before, in order for that carbon to form a double bond with oxygen, so here's my 2 carbons that had their hydrogens coming off of them. In order for us to do that before, we had to drop the hydrogen that had been down here. So now we've got a methyl group down here that we never had before. And here's the deal. This bond right here is too strong to allow us to actually do that reaction. So this reaction is not going to occur. So what about the tertiary alcohols? They don't do this reaction. So it's only the primary and the secondary alcohols that are going to be undergoing oxidation. Tertiary can't, because that methyl group, or if it was an ethyl group, if this was a longer main carbon chain, that wouldn't be able to break off, and the oxidation process wouldn't be able to take place. So no reaction. And so you can see what that looks like. Here we go. Simple as that. Okie dokie. All right, so I am going to try to do kind of a summary for you based on the degree of the alcohol that we've got. If we have a primary alcohol, and that gets exposed to an oxidizing agent, which we'll be talking about later, then that can get converted into an aldehyde. And then if we go ahead and continue oxidizing it, then that can convert into carboxylic acid. Oops. Okay. For our secondary alcohols, when we oxidize that one, again, secondary alcohol means that our hydroxyl group is just somewhere in the middle of our carbon chain. It's not at a terminal one like up above here. And so this one is just going to turn into a ketone, and it's not going to do any further converting from there. Primary alcohols, if we expose them to an oxidizing agent, will do absolutely nothing. All right, so how are your brains? I know it's different. You're not able to directly ask me any questions right here, but again, if you're confused about any of this, feel free to ask me any questions that you've got. I'm going to go ahead and clear that. And should I keep going? I think I'll go one more piece of information for you. And this is what in the world that funny little O in the brackets was that I kept drawing over the arrows. It is just a really generic way of saying we've got an oxidizing agent. And if you remember what oxidizing agents are, from our redox unit, it just means that they themselves are reduced because they allow something else to get oxidized. These are the two that are very common that I'm going to ask for you to know. And again, just to kind of got to go back to some of our older units. If it's an acidic solution, a lot of times what we're going to do with this one down here, it's a little bit wacky, but the H plus is just a reminder that it's an acidic solution because acidic solutions give off hydrogen ions or protons. They're proton donors. And then this is going to be the anion that you're going to see over here. And then they plop in usually potassium with these as the cation that goes with them. For the basic solution, it's going to be potassium permanganate. And that one is going to be, again, we have to add the oxidizing or the oxidation number into the name of that. So you can do a little bit of math to figure out if each oxygen is -2, potassium is a 1. That would make the manganese in this one a charge of 7. And so this one would be called potassium permanganate 7, but of course in Roman numerals, because that's how we like to do things in chemistry. So these are two of the really common substances. We could, if I drew an arrow, I could always do that. And that would mean the exact same thing as this. This is just generic for any type of oxidizing agent. But again, these are the specific types of compounds that we typically use for that. Okay, so a little quizzing for you. See how you can do with this. I'm just going to kind of leave it on here, and when you have your questions, because it's organic chemistry and I expect you to have some for me, just know that I'm here for you, and I'm going to continue doing these because this is a pretty cool format. So just let me know any way that I can help you, and you all please take care. I miss you so much and hope you're doing well. All right, got to figure out now how to stop this, and I'll see you on the next one. All right.